So the first thing I want to look at is basically, if you recall, our theme has been integrals around the boundary of something of the function is the integral of some derivative of the function over the thing. We have two big ones with divergence and volume and curl and areas. And this, what we're going to do is actually do a partial derivation of the divergence theorem. And it also gives us a really good idea of, and a feel, I think, for the divergence and what it does for us. For all of these, we don't really lose any generality by considering things in Cartesian coordinates and considering cubes and squares, because we're going to be building up from infinitesimal pieces. So if our little dv is a cube or a sphere or whatever, it doesn't really matter. And if you think about it by symmetry, if I have a small little dv volume here, which is a dx, dy, and dz, I will do one side, one pair of faces. In this case, I will work with this face and the one over here I haven't drawn yet, but you can imagine that whatever I do for these two works for the other two in the top and bottom. And in fact, the label is just arbitrary, what I call x, y, and z. So whatever I do has to carry through for all the pairs. Now, the other thing that's really important in these is when I consider my face, because I have a closed surface, my unit normal to the surface always goes out. That's our convention. So this one is plus j hat, because we're in the y direction. And this one is minus j hat, because it's in the negative y direction. And that's going to be true for all our pairs. Doesn't matter which really direction I take, it's positive or negative, but one will be plus, one will be minus. I'm going to consider initially my little cube having a finite delta y, and we'll take the limit as delta y goes to 0 to make it my little differential cube. So I'm going from y naught to y naught plus delta y, as I'm going in the increasing y direction. And I have some vector field f that's sitting everywhere in space, so it'll have components fx, fy, and fz. And if I want to consider the flux out of my little dv, right, by definition, we said the flux, and this is important, the divergence does tell us about the flux as we've learned, but the definition of the flux is the sum over the surface of f dotted into all my little surface elements dA. And a little surface element dA, in this case, is n hat dx dy, because, n hat dx dz, because here's dx and here's dz. And n hat is plus or minus j hat, so if I consider this to be surface 1 and this side to be surface 2, for those two surfaces, I get the following two pieces. For surface 1, f dot n hat ds, or actually I guess I've been doing dA. dA is just f sub y, because it's in the y direction for the y, because I've dotted into j hat. It's evaluated at the point x, y naught plus delta y, z, and it's got a dx and a dz. And for point 2, I take the same thing, and now I get minus fy x, y naught, z, dx, dz. And the key thing is The minus sign comes in because n hat is minus j hat. So the f dot j gives me f sub y, but it's a minus j hat, so I get the minus sign. When I'm doing it on surface 2, I'm always at y naught, because surface 2 is picked at y naught. Surface 1 is always at y naught plus delta y. But as I vary over the surface, x and z can change. And my dA is dx dz in both cases. Okay? I just want to stop here for a second and make sure that this step is key, is clear. We all good? So part of my sum over the surface is adding these. So if I'm going to add those two up, and then as I said, we're going to take the limit as delta y goes to 0. Well, what do I have? I have fy of x, y naught plus delta y, z, minus fy of x, y naught z, dx dz. What would be a really good thing to do at this point? What does this almost look like? It almost looks like a partial derivative. What am I missing? I need to divide by delta y. So I use math trick number 1. Does anyone remember what math trick number 1 is? Multiply by 1. Math trick number 2 was add 0. Okay, we multiply by 1, we don't change it. And now you can see, I mean, it's just a unit thing. We said it earlier, right? This general rule, if you look at it dimensionally, has to make sense. If my integration is over a volume, and I'm keeping track of things, and this becomes an integral over an area, you know, I need an extra derivative here to make it all work out. And notice, to turn my area into a volume, I need to divide by a delta y, thus making this a derivative. And that's why I've got the derivatives with the thing that's enclosed and the non-derivatives around the surface. It's pure dimensional arguments in one sense. And so now I have the partial f sub y with respect to y dv. And if I do all of the other terms, I'm going to get one for x and one for z, and I will get the sum over the whole closed boundary of all of my f's dotted into dA is equal to the sum over the actual volume of dfx dx plus dfy dy plus dfz dz dv. And this, of course, is just the divergence of f. And so we've derived the divergence theorem. Now, this derivation, I think, is incredibly useful because it has a deep physics idea besides just flux. If I look at this picture and I redraw it here, and I ask you the following physics question. What is the force on an element of fluid, say this is a piece of fluid, due to the pressure? How do I compute forces due to pressure? Talk to your neighbor about that. How do you compute forces due to pressure? What's the relation between pressures and forces? Okay, so the pressure is the force divided by the area. So the force is a pressure times an area. So how do I compute, here's my chunk of fluid, or myself. I'm sitting in some fluid. How do I compute the force on me? Well, if I'm in a fluid, there's pressure everywhere. Okay, so what do? So pressure is a force per area. So the force on the surface is the pressure times the area. So if I want the force on this whole thing, I presumably would sum the pressure over the area. What does that look like? What we just did. Now, however, I know, right, if I have P naught on this side and P naught on that side, is this piece of fluid going to move anywhere? What's the force term that shows up in Bernoulli's equation? Does anyone remember? Or in the Navier-Stokes equation? I mean, what determines how fast things move through a pipe? Area of the pipe. And the length and what do you have to put across a pipe to get flow? A pressure difference, right? Did it ever occur to you to wonder why sometimes we talk about a pressure difference being the force and sometimes it's a pressure? It's exactly our integral rules, right? What we want to know to make a volume move is we need a pressure gradient. Because once again, if I'm doing an integral over the boundary of the volume of the pressure dA, that means the integral of the volume has to involve a derivative. And so for a surface, it is true that the force is the pressure times the area. But for a volume element, the force is proportional to the gradient of the pressure times the volume. And it should make intuitive physical sense to you. If I have a volume of fluid, I need a pressure difference to make it move. For that volume to have a net force, there's got to be a pressure difference from one side to the other. That's exactly what a gradient is. It's the difference in pressure across the volume. Okay. So these integral relations have deep physical significance. We did it for divergence because when this is a vector, it turns out to be the divergence. Okay, and that's what matters most. Notice here, technically this is a vector direction because the dA is a vector and P is a scalar. And the gradient times the volume stays and keeps your vector sense. Okay, so you get a correct direction out of both of these. If there is a pressure difference across your areas, you will get a force in a certain direction given by that. And in fact, this is actually even more advanced. It's really one component of the stress tensor relation that comes into turning things and doing things in the fluid. But it's this very critical idea of the relationship in physics between what happens at surfaces versus the volume the surfaces contain. It's a fundamental physics idea as well as a fundamental math idea. Any questions on that?
How does the area version, the pressure gradient from one side to the other of the volume makes a lot of sense, but I don't understand the picture,
Well, this is looking at it from, if I keep in track of Newton's third law, every little piece inside my volume has to be equal and opposite and cancel. So at the end of the day, all that matters is what's the pressure on the right-hand side, what's the pressure on the left-hand side. And the difference between these two, all right, that's what this integral will do for you. Because one of the dAs will be to the right, one of the dAs will be to the left. Right, and you'll get the pressure difference. This sums up all your little gradients within the volume. Again, as you do the full volume, all the little pieces on the inside cancel, and you end up with basically just a difference from one side to the other. And that's the beauty of thinking about it in terms of either the volume or the surfaces.